So we've been talking a little bit about the intermediate value theorem, and while it seems like a bit of a banal result, it's actually a lot deeper than it looks like at first blush. It can tell us some pretty strange and fascinating things, and it's of importance to in a more theoretical context as well. But the example we're going to look at right now is a bit of a classic, and it's stated as follows. On Earth, there are always two antipodal points that have the same temperature. So antipodal just means polar opposites. So completely opposing points on Earth. And I'm assuming that the temperature varies continuously. So this isn't a an unreasonable assumption. You might expect that if a temperature is something at one point, then everywhere around it's going to have roughly the same temperature. But we're going to assume that, and that's necessary for use of the intermediate value theorem. But how can we leverage the intermediate value theorem here to help with this? Well, we're going to start by modeling the problem. So step one, I'm going to take any great circle. I'm going to simplify it so we have a whole sphere or geoid to work with, but I'm going to just take a great circle. And it could be any great circle. It could be, for example, the equator or a line of longitude or something like that. And I'm going to, let's draw it out. So here we have a great circle. And I'm going to pick a point on that circle P. And we're going to parameterize this circle by saying any other point is just some angle theta away from P. So now I'm going to define a temperature function along this great circle. So I'm going to define T of theta to be the temperature at the point which is theta from P. Be along the surface or up in the atmosphere. It doesn't really matter. And we'll note that T is continuous and is defined on 0 to 2 pi. Why is it continuous? That's just because we're assuming the temperature varies continually. And we'll make a last observation that T of 2 pi, of course, is just T of 0. And that's just because if we go around the whole circle, we ended up right back where we started. Okay, so now we have a temperature function that we can play with. Step two, and define a function d to be the difference of t of theta plus pi and t of theta. Okay, why am I doing that? Well, let's draw another circle. So let's say I have some p and we have some theta here. Well, the angle theta plus pi is going to look like the exact opposite point, the antipode to the point theta. So this is the antipode to theta along the great circle. So I'll note that I'm going to define this on the interval 0 to pi. And I'm going to make a remark here. Note, if we can find some theta such that d of theta is 0, then, well, what does that mean? Well, it means d of theta is 0, but d of theta is t of theta plus pi minus t of theta. So I can flip this over and say that therefore t of theta plus pi is t of theta for that theta. So we found two antipodal points with the same temperature. Okay, but how are we gonna do this? I'm gonna point out also that d is continuous since t is, and it's really just a linear combination of t and itself with some kind of shift happening in the argument, but it's a continuous function. And that's going to be necessary to use the intermediate value theorem. Okay, so step 3, I'm going to note that if d of 0 is 0, then we are done. That's just because of what we mentioned up here. All we need to do is find one angle where d is 0. So if 0 is that angle, then the point P and its antipode up in our great circle drawing up here will fit the bill, and we've proven our claim. Okay, so what about if D is not 0, or if 0 is not a 0 for D? Let's just assume that it's negative. It doesn't really matter. The same argument works in reverse if it's positive, but let's stick with it being negative for now. Then we can note that d of pi is t of 2 pi minus t of pi, which we saw was t of 0 minus t of pi. And I can factor out a negative, and that's going to become t of pi minus t of 0. But that's actually just d of 0. So if d of 0 is less than 0, then negative d of 0 should be greater than 0. But now I have a continuous function. So d is continuous on 0 to pi, and d of 0 is less than 0, and d of pi is greater than 0. So the intermediate value theorem applies and says that there is some theta naught in 0 to pi such that d of theta naught is 0. And for the reasons we mentioned above, that actually proves our claim. So we found in two antipodal points that have the exact same temperature. Now, what I find fascinating about this is you can think about the actual practical situation. This is probably impossible to actually measure. For one thing, the temperatures are going to be constantly changing. And how do we even measure the temperature at a point anyways? We would need some sophisticated measurement techniques. But what's I find so profound about this is that even though we couldn't measure it, we can still know that it's true. The math is telling us a fact about our world that we have yet to have the ability to measure.